of course, I'm very lucky because everything that was, a lot of the things that I'm going to be really sloppy about talking about have been spoken about in far more detail with far more rigor and intelligence than I was going to do. So that's going to be perfect. This is joint work with Michel and my students Sohail Faizi and Murial Medard. Yes, I managed to find another student named Muriel. This was not easy. First met her because she was getting emails from me because people were sending things to muriel@mit.edu, and that was her. But it's mainly Sohail's work. As I said, it's a practical approach, so it's going to be fairly simple and applied. Unlike what was said this morning, that they were like, that there generally are no curves. There actually will be curves here. And the idea here is it's fairly simple, and other people have done this, I think, very aptly. So we're just adding to the literature and trying to compare compressive sensing and information theory. Now, you might say compressive sensing originally did appear in the information theoretic literature. So, we sort of claim it for our own, but it's not really that information theoretic at its core, in the sense that it's really looking at low complexity approximations of signal constructions from incomplete and contaminated measurements, but without the use of coding techniques at all. Right. So it just obviates the whole use of coding, which generally forms to some extent our bread and butter in information theory. So there's been a lot of work. I'm not even going to try to do a good job at mentioning it all. Probably the work that is closest in spirit, and have a typo, I have an extra S, is the work by Xava and ad-hoc from 2007. But basically, this is what we're going to do in this talk to try to show why, in at least some. So I'm not going to try to combine compressive sensing and information theory at a high, in some sort of particularly deep way. What I'm going to try to do is I'm going to start building from compressive sensing approaches, things which we already know how to build, in order to get to something which generally we don't quite know how to do, and show that at least compressive sensing gives me a reasonable suboptimal approach, a good heuristic. That's it. That's all we're going to do. But in so doing, I hope that I'm going to make some connections which are interesting. So I'm going to start out by doing something that nobody in his or her right mind would do, which is take compressive sensing just to do point-to-point channel coding, which you definitely don't need to do because we all know how to do that. From there, then show how you could do source coding, or at least wave my hands to show how you could do it. From there, then move one step up to go to source channel coding. From there, move one step up from the source coding to do Stepien-Wolf distributed source coding, which I mentioned briefly in the tutorial on Thursday. From there, build up to multicast networks. And from there, build to joint source channel network coding for multicast networks, which actually should, in some way, I hope, harken back to the first talk of this workshop, which was Michel's talk. So maybe it will sort of come full circle in some way. Okay, so let's start with point-to-point channel coding. So when I have channel coding, I have messages, and I channel code them, and they go through noise, and I channel decode them, right? So this is hardly new. But the idea here is that I could maybe use compressive sensing, because really what I'm doing in channel coding is I am going to add some sparsity in order to be able to reconstruct, right? And channel coding is an interesting way of adding the sparsity in such so that I get close to capacity. So what would happen if I was able to add some of the sparsity in a way which would lend itself to a compressive sensing reconstruction? Right? Now again, this is not how we usually code, but what if I did? Well, it's clear that if I rely only on that, it's going to be a little iffy. However, we are used to sort of souping up our codes by having an inner code and an outer code, right? So if I can do something which is kind of like a concatenated code, then maybe one of my codes can be a little wimpy. That's obviously going to be the compressive sensing based code. Maybe one of my codes can be a little wimpy, and overall I might not do that badly, right? So that's the intuition. So let me start with that. So I have a k-sparse signal vector, okay? So let me start by giving a little bit of background on compressive sensing. Again, this is going to be extremely high level, and most people have seen this. I would say almost everybody has seen this in some guise or another. But the idea is that I have a k-sparse signal vector, and that k-sparse signal vector goes through some matrix G, which is an n by n matrix in such a way that m is much, much less than m. And it's going to be corrupted by some noise. And the reconstruction method, there's several reconstruction methods. We're going to use lasso, is the following. Again, people have seen this very often. The only thing to point out in case you haven't seen it here is the fact that you have an L2 norm there and an L1 norm there. And if G satisfies a restricted eigenvalue condition, okay, then actually you can say something about the reconstruction from the lasso conditions. I'm going to generally call this cal L, okay? And so y tilde is a reconstruction, which is just the argmin of this metric. And then you can say certain things about it. Now, I'm just going to put a little aside here. The original work, of course, dealt with the work by Countess Donohoe, which I'll talk about later briefly, dealt with doing a restricted isometry property, right? The restricted eigenvalue condition is a little more general, okay? And the reason I'm going to use it, you'll see later, is because we got stuck using our IP, and we needed to use something a little bit more general. But the restricted eigenvalue condition, really all it says, and we'll see this picture later again, is just that I want to have a high loss curvature so that I can control error, right? So I want to make sure that if I have a small delta in my cal L, in my metric, that means that my y and my y hat are not too far away. Because if the curvature was flatter, then I could have a small difference here in that metric, and these things would be far apart, right? So it's very intuitive as to what's going on in there. So that's why you need that condition. And basically, I'm not even telling you exactly what the directions of sparsity is, but it's just saying that these eigenvalues should be bounded away from 0. And we're going to reuse this later because we're going to be doing some compositions of matrices, very simple compositions of matrices. Okay, so just as I mentioned, the restricted isometry property, it holds whenever the RE holds, and the RE is actually sufficient, restricted eigenvalue condition is sufficient, even though people usually use RIP, but it turns out that if you start doing, as I said, things that are a little bit more, when you start processing a little bit more, this is more fragile than this. So that's what we're going to be using, the restricted restricted eigenvalue property. Okay, so let's go back to the channel coding. Having done that tiny little loop away to look a little bit at channel coding. So I have my AWGN channel, as I said before. What I'm going to do is I'm going to create a random sparse vector. This is going to be my source coding, okay? So clearly if it's random, I'm going to need a maximum likelihood decoding, which is going to be high in complexity. And then I'm going to pass it through another matrix, which is going to satisfy the restricted eigenvalue. That's it, properly, okay? So I can always do this with high probability. And then I'm going to map it using this projection which satisfies the RE condition. Again, think of an inner code, which is a really good code, and an outer code, which is an insane code that nobody would ever use. All right? So at the decoder, what I'm going to do is I'm first going to do a compressive sensing decoder, right? And then I would do an ML decoder. All right? All right, so basically I have a two-layer code, as I mentioned, my outer layer and my inner layer. My inner layer is a really good code, but it's more complex. My outer layer is not complex in terms of reconstruction. For instance, lasso has low complexity, but it's certainly it's certainly not the kind of code one we usually use for coding purposes, right? And again, remember that when you're talking about reconstruction, generally, if you come from information theory, you'd say, well, why don't you code it, right? Why are you just using whatever redundancy happens to be there rather than coding it? Okay, so So here's a very simple result relating at high signal to noise ratio, and I'm being extremely sloppy about what I mean by high signal to noise ratio, but I may get less sloppy later when I look at the network, or if I have time towards the end of the talk. So this is, if I look at the channel capacity, and if I look, again, I have this inner code and this outer code, the rate that I can achieve with asymptotically vanishing probability of error is going to be a portion of the rate achieved by the inner code, right? So and if I only used an inner code, I would have C, right? Because that's the best code, that's capacity achieving, all right? And then there's a rate achieved by the outer layer code, and then there's some combination of the two. So at least it's scaling as C, okay? Now, why would I ever want to do that? Well, the decoding complexity, if this is normalized complexity according, symbol per second, the decoding complexity of the inner layer code, which is the maximum likelihood, is going to be modulated by this K. Remember that the K is basically how powerful what I'm doing here in my inner layer code. So I'm controlling that. And the decoding complexity of the outer layer code here is going to be, in a noisy setting, the decoding complexity of a compressed sensing decoder. Okay? So I'm mixing a bit of the two. So if I lower this, it's going to be a little lousier. I'm not telling you how the alpha relates to the K. Obviously it does, right? But it's a little complicated, and I'm not showing it to you. Okay? But all it's saying is I could use a construction where I create a signal that lends itself to treatment by compressed sensing in order to have a lower complexity decoding. Okay, so the higher the decoding complexity gain, the higher the rate loss. So again, I would never do this for source coding, but for channel coding. But maybe I could think of, whenever I do channel coding, I can think of doing the reverse, the dual, which is just the source coding. So I could think of doing the sparse channel coding, and the reason I started with that was because it's closer to the original compressed sensing problem. Or I can think of doing source coding, and if here I was doing first a channel encoder and then the CS encoder, what's going to happen here is I'm first going to do the CS encoder, make it sparse, right, and then put it through the source coder, right? This is basically, I'm sparsifying it over here, which means it's going to be easier at this level to do things. Does it make sense? In the same way that with the channel code, I was using a wimpier channel code as the inner code, right? So I'm not going to go into the trade-off that you have here, but I'm going to jump directly to the fact that if that is to happen, if I can sort of modulate, if you will, the sparsity jointly with, by two different methods, one which is the channel code or the source code, and one which is a compressive sensing transformation of the signal which lends itself to compressive sensing, right? Then clearly I can combine the two. Now, again, why would I want to do this? I have separation between source coding and channel coding. I know that, right? I don't need to do them together, but of course there's a large literature on doing it together. One of the reasons is that, I might be wasteful here in terms of my complexity, because I'm going to take an X which has some naturally occurring redundancy in it, say temporal redundancy, and then I'm going to squeeze all the temporal redundancy out, and then I'm going to put it through a channel coder, which is going to add redundancy, right? So I first squeeze every last ounce of redundancy, and then I add it. Now, of course, the naturally occurring redundancy might not have been the right redundancy in the first place. That's for sure, right? It might not have been the kind of redundancy that helped me with the channel coding. On the other hand, whatever happened to be there that might be helpful, I don't necessarily want to squeeze out, right? So this is allowing me in a way to modulate the two a little bit more subtly, okay? And the very simple approach that you could use here, for instance, is so I consider an AWGN noise, and I look again at the highest now regime where, yet again, I'm being extremely sloppy about what I mean about this. I could basically think of having a source node which is transmitting a random linear combination of its measurements, okay, and then just using a compressive sensing decoder. Okay, and that's going to give me some sort of rate distortion. So, by the way, when we were doing this work, we just blithely went along, and then we assumed that there would be a lot of readily made regularization parameters here. Yeah, well, okay, Maxine laughs. Yeah, well, it was pretty funny. There weren't. So even for something this simple, and I don't know if it's because we were looking at a slightly different problem, because we were looking at a channel coding problem, which is and source coding problem, which is not what people generally look at. But we didn't find many. So anyway, I'm not showing the details here, but just as an aside, and again, maybe I was the only one in the audience for whom this was unexpected. Clearly, it was not unexpected for you, but we actually found it pretty hard to get good regularization parameters. Okay, so by the way, everybody knows what MSC is. PRD, which is the percent root mean square difference normalized, is something that when I was talking to colleagues that do compressive sensing for medical applications, this is something they use a lot. So again, maybe some of you are familiar with it, but it was interesting. So anyway, you see two rate distortion regimes. So above a certain rate, you have almost constant distortion, and then below a certain rate, you have a rapid distortion decrease. And if you look at the rate distortion as a function of the sparsity level, one of the things that you can see is that the number of measurements grows almost linearly with the sparsity ratio. Okay, so remember this is the K, which is the original one, and this is the M. So anyway, it was interesting to see what happened with MSC and PRD. I didn't even know if they were that different with respect to each other, and they really are. The behaviors is very different. All right, so this is just to say I could use this compressive sensing approach reasonably to do something which gives me some sort of rate distortion. Okay. That's it, right? At this point, that's all it is. Again, why would I ever want to do that? Well, let me step up a little bit in complexity, and I'm going to look at a Slepian-Wolf encoder. Now, why would I want to look at a Slepian-Wolf encoder? Again, I know how to do Slepian-Wolf encoding, right? So presumably, I don't need to go to something like this. But let's see whether, because it's fairly easy to do in terms of the decoding, there would be some good reason for doing this. Okay, so the only reason why I might want to use a compressive sensing approach is because I have enough sparsity here somehow at the sources, right? So basically what I'm going to rely on here is two levels of sparsity. What I was relying on before was a temporal sparsity, and what I'm relying on here is going to be both a temporal sparsity and a spatial sparsity. Right? I mean, if these guys are highly correlated, then that's not going to work. I mean, maybe it's going to work stream by stream, but it's not going to work across them, right? So I'm going to see whether I can use source coding such as I did individually here, because we know that with Slepian-Wolf, what you're doing at each source is pretty similar to what you're doing as if the source were roughly by itself, even though it's not by itself, right? So that's the intuition. And whether there's enough spatial sparsity here to actually make the thing work out. Okay. So let's see if that happens. So, but what I'm going to have here is that each source is going to transmit with a small probability, where n is the number of sources, and m is the smallest number, which is going to satisfy the compressive sensing inequality that I put up before. Okay, so remember how we talked about these two levels of sparsity? So the way I'm modeling the sparsity, and I'm not saying this is particularly good, but you know, it is something. It's that I'm going to have a low probability of active sources, and I'm going to have a very high probability of inactive sources. Okay, I'm not dynamically changing these. Okay, I think you could, but right now you basically pick once whether the sources are active or inactive, and then you go with that. All right. So I have these. I have the different sources. They're going to have their own sparsity characteristics here. And what I'm going to do is I'm going to have the receiver decode the messages that were sent. So obviously, just from the inactive sources are not there, just from the active sources. And then it's going to use a CS decoder to try to recover the ones that were not transmitted. Okay? So basically, this is how I'm reducing the rate. Right? So as opposed to reducing the rate in the usual Steppenwolf way, I'm just turning off some, yes?
What does the inactive here means? That
so I'm just going to turn them off. Once and for all, right. I'm basically sampling among the sources.
So this is just a subset of the...
exactly, yes. I'm going to sample them randomly.
With the distribution, which is the marginal distribution. Of
yes, exactly. Exactly. That's exactly it, right? So, and I'm going to sample them in such a way that I can use the CS decoder to recover the untransmitted ones. And that's why I'm just turning them off. Right? I get to pick those. I get to pick the ones that are inactive. Right? I'm picking them randomly, and I pick them once and for all, but I get to pick them. Right? So in the same way that, you know, compressive sensing is basically a sampling approach, that's what I'm doing. I'm just turning off some sources completely and just sampling the others. And the reason I want to do this randomly is because the sources are not communicating with each other as to who's sending and not. Right? So each source is source coding independently, and part of its source coding is whether to transmit or not. Which sounds a little weird, right? But anyway. So if I were to ignore what's happening among the sources, I would need to transmit all n. Right? But I only send m because I don't really care. Of course, there's some probabilistic approach there because, you know, I'm choosing them randomly. Okay. So basically what happens is that if I look at the required min cut rate for this distributed source coding, all I need is a rate which is no less than the sum of these Mij, where the Mij are the active sources, right? And right now, I haven't told you at all whether this is good or, you know, even close to as good as regular Steppenwolf, which would be the joint entropy of all of these sources. Okay? So I'm just saying you could do this, and you could reconstruct them. Whether this is actually small or not, I haven't said. Right? Okay, so just to give a comparison, why might I want to do this? Again, let's think of the decoding complexity. So if I'm doing compressive sensing and independent coding, the mean cut that I need, right, and I'm ignoring the individual constraints. Let's assume that each of these has enough to send the rate of each. Otherwise, you know, obviously the Steppenwolf polytope will screw. I mean, it's not a polytope. It's, you know, the region will screw up. Okay, but you know, if I'm looking at the sum, all I'm saying is that the min cut here has to exceed the sum of the entropies. Okay. And of course, if I was doing Steppenwolf, then as I said before, it would be something where I would have to do, where I would just get away with the minimum, which is the joint entropy. Right? Now, of course, you could say, maybe that was a little dumb. You could have done, just like you were doing for a single source, you could have done compressive sensing and Steppenwolf, right? And still gotten the joint still gotten the joint entropy, And again, I hadn't shown you for the single source how that worked. I've only showed you for single source coding. I only showed you for channel coding. And it's true, you could have done that. But basically, what happens is you still have this Steppenwolf complexity here. Right? You're not really getting away from it that much. Okay, so it's still difficult. It would be a little easier, maybe, than doing the traditional Steppenwolf, right? But I'm not getting necessarily a big gain. I'm not getting the case where I really am able to do everything independently in terms of the decoding. So if I were to not turn off the sources, which again sounds like an insane thing to do, then what I would have is I would send all of the sources. I would have naive correlation ignorance, and in that case I would need the entropy of each source, the sum of the entropies of all the sources, right? And then I know how to decode that. So the main thing that happens here, the main thing that happens here is that these look similar, but remember these are just the active sources. These are all the sources. And if I look at the complexity here, n is much bigger than m. Okay, and here I would have this complexity with n. Here I have a complexity with m plus this, which is relatively less complex. Okay? And this rate should be much smaller than that rate, because the n is much less than the m. So that's it. All I'm saying is I'm doing something which is simpler than the naive correlation ignorance and doing better. But it's not optimum. And I could have used compressive sensing to do something optimal, but it wouldn't have bought me as much in terms of complexity. Does that make sense? Right? So it's kind of okay. You know, I got something almost for free, right? Okay. So in order to get a little bit of idea, you know, how much this buys me, I just want to show this is for two sources, and I haven't told you how correlated they are. I think rho is 0.5 in this case, but just to show you that even here you can see this is for PRD. If I look at the rate distortion, the case for ignoring. So T is just temporal, because of course you always want to take away you always want to shed the temporal redundancy in the source coding, and so this is temporal plus spatial, and this is just temporal. Okay, so these curves here, the thin curves, only look at the temporal, only compressing individually each source, and the temporal plus spatial is compressing each source, and then basically turning the things off to take into account the spatial correlation. So this turning off of sources is helping me. Right? As crude as it is, it's extremely crude. Right? I'm just not allowing some sources to transmit. And the same thing if I look at MSE. Okay, I get the same kind of improvement. So it's not the same as the full, narrowing it down all the way to just the joint entropy, but it gave me something, and in some cases it's not going to be too far. Okay, so let me now look at a network. So let me now look at a multicast network. That's to say, this is going to be a network where each receiver wants to reconstruct all of the sources. Okay, so I had a multicast network in Steppenwolf, of course, as I mentioned when also gave the tutorial. It's a completely degenerate one. It happens to have a depth 1 and a single receiver. Okay, so it's not the very interesting multicast network, but it is a multicast network. So now suppose that I have an actual multicast network, and suppose that my multicast network has some arbitrary topology, but I have no noise in it right now. Okay? Well, actually then the problem becomes a little bit more complicated, because you could say, okay, why don't you first do the source coding? Steppenwolf, whatever you were doing there was, crude, but gave you something. And then, you can do the random linear coding inside the network. That's very easy to undo. So you should just be able to then undo the random linear coding. And after undoing the random linear coding, you should just be able to get back to to the original sources, doing whatever you were doing before. Now, the problem is, in general, that there is no separation between source and network coding. This results by Murty and others, including Michel was part of that work. So I don't want to remove all the spatial correlation. Right? I don't actually want to do that. And the reason I don't want to do that is because, so, you know, if you look at the sensor network literature, there's actually a fair number of papers that are trying to do Steppenwolf to remove spatial correlation, and then they transmit over the network using routing or whatever. But if we always wanted to remove correlation at sources, you know, Akamai would be out of business, because why would you ever have mirror sites if you never wanted correlation at sources? I mean, that's the extreme version of correlation. You actually copy the source. There's a benefit in the network to having a source close to a particular receiver. Right? I mean, it's as simple as it sounds. So, you know, you don't actually want to remove the correlation willy-nilly. The spatial correlation, not. The temporal, for sure, right? Unless it's going to help you maybe with the channel coding. But right now, I don't have noise. Okay? So what can people do? Well, so we know that if I use random codes, I can actually get to the min cut. So as long as the joint entropy does not exceed the min cut, I can actually get arbitrarily closely I can get to asymptotically error-free reconstruction. But, you know, going back to Alain's talk, this basically becomes a method of types argument, right? So the decoding is difficult. The decoding is difficult. The decoding, as I mentioned in the tutorial, the decoding becomes a minimum entropy decoding, which is hard by itself. It would be NP complete. If you allow an extra error term, which only grows as, if you allow an extra error term which is really no larger than the error exponent, which comes from the fact that you're doing fixed length coding anyway, then actually you can get something that's polynomial time, and actually that was part of Todd's work in his thesis, but the codes are really, really, really long. Okay, so it's polynomial, but you know the constant that's in there is, you know, it's called a constant, you know, out of politeness, right? It's not, you know, you're basically building this massive code, right, like inside the universal code, and then it's polynomial in that. But it's sort of like the innards, you know, the innards are already so long that it's that it's scary. Or you can also build specific codes, but maybe on small topologies. Right, so the topology is not that big. You can do it jointly, non-trivial, but not that big. Okay, so this is just to say that already the problem is getting a little harder, right? Remember when I started with channel coding, you're like, what on earth would you even use compressive sensing for channel coding? I mean, we don't have to, even for source coding, right? Slepian-Wolf, the Slepian-Wolf example, you could argue, well, you know, if you really have a lot of sources, it might start getting a little hairy to do regular Slepian-Wolf, you know, just in terms of the decoding and so on, right? I mean, at least I haven't seen it done in practice. So there you could say, okay, there it makes sense. Here, at least we're starting to get to a problem which by itself is a little ugly. So what happens? Well, what's going to happen is I'm going to combine some of the things we've been doing up until now. I'm still going to have the sources transmit with a certain probability, so I'm just turning them off. Right? So this is not a very complicated source channel source network coding. The intermediate nodes are going to perform random network coding, and the decoder is first going to decode those, which again is just at this point is just Gaussian elimination, and then it's going to use a compressive sensing decoder to recover the untransmitted ones. Okay? If there's a fair number of sources, then you know the whole problem of whether I shouldn't have turned off some sources or others in general will you know, there are issues there, but it's I'm not going to talk about them. We can talk about them later. But at least one of the things that you get is, instead of having something which in the classical extension of Slepian-Wolf to a network, you would say I need the min cut to be the sum, to be the joint entropy. Here you say I need the min cut to be greater than this number, which again is the number of active sources. So at least it's a parallel to what was happening with the Steppenwolf case, but in a situation where it would have been much harder to do it without a compressive sensing approach. Okay, so finally getting to the topic of the talk, which was a practical approach. So I've just been building it up, right? So we built it up from channel coding. I kind of vaguely hinted to source coding for a single source, then on to Steppenwolf, then from Steppenwolf to the extension to multicast without noise. So the problem that we're actually going to try to tackle, at least is a problem which I really wouldn't know how to do. Okay, so I have a reason for doing something suboptimal in the sense that I really don't know how to do something optimal. So if at least I find something suboptimal which is reasonable, then, I've done something, I see. Okay, so what I'm going to have is, I'm going to have a set of sources, and they're going to have temporal dependencies per source, and then I'm going to have spatial dependencies, just like in Steppenwolf. Okay? Just like before. And it's going to go through a high signal to noise wireless network. And what I mean by a wireless network here is I only have multiple access channels and degraded broadcast, physically degraded broadcast only. That's it. Okay? And AWGN link. So going back to Michel's talk, if I had only point-to-point channels, then we do know exact sorry, actually it shouldn't be just with point-to-point channels, with multiple access channels. So I would have exact separation, or in the case of multiple access, in some case of broadcast, and Michel had shown those pictures on yesterday, then I would have separation between source and network coding and channel code. That's to say, the source coding and the network coding are still not separable. But I would have a separation between the source-network coding on the one hand, and on the other hand, the channel coding. Right, so remember Michel's talk on separation. However, it's not constructive. So I know that I can do them separately, doesn't necessarily mean that I know how to do them. Okay? There's been a lot of work, I'm just mentioning Medard, but of course the many other people who worked on this, on noisy network coding. But noisy network coding uses independent sources. At least all the work that I've seen. I'd be interested to know if anybody else has seen anything like that. So the question is, if I have something like this, what do I do? Because even if I wanted to do a separation between the source coding and network coding on the one side and the channel coding on the other side, I don't exactly know what to do, when you give me the entire network. I can tell you that, there are equivalences, but exactly how would I operate this efficiently? Okay, so recall the restricted eigenvalue condition, which was basically just a condition on this thing being, kind of curved up sufficiently tightly, right, rather than flat. All right. So this is what I'm going to do. So whenever I'm using any of these network coding approaches for multicast, I'm always just doing something linear, right? It's all linear. So the question is, if I go through a bunch of linear transformations, am I still going to be able to do my reconstruction using compressed sensing? And it seems so trivial. And it probably is for somebody else, but it took us a while. And actually, that's why we had to go to the RE condition. We couldn't get to work with RIP. If anybody has an idea of how to get it to work, be welcome, because of course RIP is sort of a more user-friendly, certainly more common approach. We could only get it to work with the RE condition. Okay, so so basically all this is saying is that you can linearly cascade. And as long as your eigenvalues of the matrices which you're using to cascade are not doing anything awful, your curvature will remain okay on this Cal L, which makes sense, right? It's sort of very intuitive, but like I said, it sort of took us a little longer, frankly, than one would have expected or hoped. Okay, so now what am I going to do? Well, I'm going to have my temporal dependence, right, along each of these sources. I am going to have my spatial dependence, and then I have to figure out what to do inside my network. So remember, when I had no noise and I had the multicast network, when I had no noise, I just did random linear coding, and I knew that that got me to the min cut, right? But here, I don't exactly know what to do in general. Anyway. Okay? So what I'm going to do is I'm going to do something which is called analog linear network coding, which sounds really fancy. It's just amplify and forward. Okay, so we'll see that in one slide. Okay? And the nice thing about amplify and forward is amplification is linear. Okay? At least the amplification we're going to use here. Okay? So we're going to use that deep insight. Okay? So I have the joint source channel coding. I'm using random projections to transmit subspaces. I'm going to do my really fancy pre-coding, which is turning off sources. That really sophisticated kind of pre-coding. Then inside the network, I'm going to do the analog network coding, which is, again, just amplify and forward, okay? And then I'm going to do compressive sensing decoding, taking into account both the spatial and temporal decoders, like I did with Slepian Wolf. So that's why we were building it up, where we're just sticking the whole thing together. So remember, the first thing that I did was channel coding at high SNR, which, of course, was a linear channel because, you know, it went through, you know, it was 1 times x plus noise. And basically what we're going to have here, where the noise was somehow going to 0, what we're going to have here is some matrix instead of 1 times x plus noise. And the matrix is given by the topology of my network, just like when we're doing non-analog network coding. So let me just do a small aside as to say what I mean by high SNR. And at first you would think, well, high SNR means that the signal to noise ratio is high. Thank you. You know, that was really useful, Muriel. And in a point-to-point link, there are many ways to get into high SNR. I can get to high SNR by bumping up the source's power. I can get to high SNR by reducing the noise, or I can get to high SNR by bumping up the channel gain. All of these are perfectly equivalent. I can't tell the difference, which is why, you know, it all has the same effect, which is why people all the time go to high SNR by doing any of the following, right? It doesn't matter. Usually you normalize the noise and you let the power go up. In a network, however, it doesn't extend. You don't have a single network signal to noise ratio. And as many of you are aware, maybe all of you, there's been a fair amount of interest in high signal to noise ratio networks. So actually, this is a network that Michelle had brought up in her talk, which is Brett Shine's thesis, which is this diamond network. So one way of getting to high SNR, which is the way that Avestimer, Degavi, and Shea take, is that they let these A's go to infinity. So suppose that I have a network, and the gains are all related with these A's, which are just, you know, some powers. I'm going to let these A's go to infinity, and then I'm going to see what happens. Okay? What they get here is that they see that there's a discrete approximation to this kind of channel, right? That's what they use. So that's why they get this discrete approach. And there's a bounded gap away from capacity, but it's a bounded gap that grows with the size of the network, and it's also a bounded gap of half a bit per degree of freedom, so per second per hertz. So as your bandwidth goes up, so does the gap. Okay. Suppose instead, if I'm in this network, that I keep the A's constant and I bumped up the source power, not touching the noise in either case. Now, if you think of what you're doing in a network generally, you don't get to control the noise in most cases. You don't get to control the gain, certainly not if it's a wireless network, because even if the gains were originally related in the following way, A cubed, A squared, A squared, and as they show up, how could I scale it that way? I mean, I could try to bring the nodes back together, but even if I bring the nodes together more and more closely, how can it somehow always stay with the same relation. Right, so even if the way I was thinking of bumping up my SNR is by somehow shrinking my network, I can't in general do that, and I can't do it for this simple network, let alone over a larger network. Right, there isn't some sort of transformation to shrink it down and keep all these gains this way. If you take some sort of square power law, whatever. So suppose that here instead I increase the transmit power. Then the analog network coding, which is really amplifying forward, is actually going to achieve capacity. For instance, in this case, if you look at what the capacity is, let's look at the SNR at the destination. So the min cut here is at the destination. So I have the gain from relay 1 to destination, the gain from relay 2 to the destination, and then I have the noise that I'm dragging around. This is the unit noise. Right, I'm going to have the unit noise, and then I have the amplification, basically here of noise from before. Okay, so this is just the SNR at the destination, and if you plug in these a squares and a cubes and so on and so forth, what you'll see is that the dominant effect is going to be the a cubed. Right, so I'm going to take a cubed squared, and I get 1/2 log of a cubed a to the 6th, so it gives me 3 times log a. Right, that's the usual sort of highest SNR min cut. Okay? And so as my source power goes up, if I keep these P1 and P2 fixed here at 1, and I keep my gain fixed here at 10, what you see is that this is the MAC cut set bound. So the multiple access channel at the destination is the cut set bound, then it's one's approaching the other. Okay? Okay, so at this point, I'm just going to give you the result, which is that to satisfy for each source this kind of distortion, all I need is a number of network uses, which scales in the following way, which is exactly what we were seeing before, except now I have 2 terms. I have one term which relates to the temporal sparsity, K1, and I have another term which relates to the spatial sparsity, K2. And if I were ignoring the correlations, I would get something that looks like this. And remember, K1 is much, much smaller than little n. K2 is much, much smaller than big N. Right? So I've had a number of uses in order to get to that distortion, which somehow, even though I didn't know what I was doing inside the network, but I'm under the high signal-to-noise ratio regime, was much better than not having done anything and just gone through the analog network coding. Okay? So that's it. Basically, there was a problem where legitimately I didn't quite know what to do, and at least legitimately I could say that I could do something. All right, so that's it. We presented one connection. I mean, there are many between, compressed sensing, traditional information theory. Compressed sensing maybe is a reasonable way to obtain certain simple approaches to certain difficult problems. Again, I started out with channel coding. I would never somehow suggest that one use it for channel coding. It was just to sort of build up in the high signal-to-noise ratio what was happening and bring the whole thing together. And so you can show that, it's sort of a simple approach to all of these simple problems. And if you munch all these simple problems together, at least for a problem that's not simple, you get something that makes sense. That at least you can say something with, you can take some information theoretic simple problems, put them together, and say something about a problem which we don't quite know what to do well from just an information theoretic point of view. And that's it. Thanks. Any questions? Yes?
I didn't quite understand the concept of network uses.
Yes. Oh, okay, yes. So it's the number of samples, the number of uses that you do in the network. So it's just the number of degrees of freedom. Sorry, that's my fault because I did a lousy job explaining it. It's not you, trust me. Yeah, but people use that quite a bit in some of the CS literature, and it's my fault. I didn't give enough background. Yeah. Okay, other questions? Yes, Maxine.
Are there any connections to the work Andrew Barron was doing with his student, whose name is Anthony Joseph, on these superposition codes?
Ah, yes. That's a good question. I don't know. So, I'm not quite sure how it would do here.
Right. Yes.
Right.
Yeah.
So for the other stuff, I think one could probably use it, right? So in case people did not hear the question was there any connection between this and the work by Barron's group on superposition codes, right? So you're right that they have an approach for this side, right? And again, as I said, there were many other approaches which I didn't mention in my willfully neglectful, but at least honestly neglectful overview of compressive sensing and information theory. But I don't know how to do that here, right? So the reason we built it up this way, which sounds terribly naive, is remember we started with channel coding at the high SNR because eventually I needed to put the channel code. So I started with channel coding, and then I made it look like I was just using that just to go to a single source coding. But actually, it's because I needed to get back to it for this. But it's basically channel coding, it just becomes an ISI channel. That's all it is. It's just a glorified ISI channel once I go to the analog linear network coding. So I don't know with the superposition codes what would happen here.
Yeah, it's not clear.
It's not clear. So that's a good question. I think for everything on the left, probably it's a better approach than this one, but I wouldn't know how to combine it. Maybe there's a way. That's a good question. I just don't know. Yeah. Yes.
My question, kind of a general, basically, is a NP-hard problem.
I'm sorry. Can you speak a little more loudly?
My question, kind of general.
Yes.
It's like solving NP-hard problem. Suppose I design a channel coding, which does not exist in literature. So it requires NP-hard algorithm to solve it because it does not have good structure, but it has very nice property. It can utilize unstructured source distribution, for example. Okay, so I'm designing joint source channel coding.
Okay.
But the decoding part is NP-hard problem.
Okay.
So suppose I want to solve this NP-hard problem with compressive sensing approach. So I want to have a sparse coding. So I do sparse coding, and when I do decoding, it's noisy. Right? It's noisy. So I try to estimate what kind of source code has been transmitted. Joint source channel code.
Right.
The problem itself is NP-hard because I've tried all these possible combinations.
So the answer is I don't know. I don't know whether people have looked at these approaches in order to, I mean, so what you're saying is, are you looking at, so just like minimum entropy decoding is NP-hard, so is, maximum sample mutual information decoding, right? The reason I was using compressive sensing here was not to solve an NP-hard problem, was to justify using a lousy approach because the alternative was just too horrible to behold, right? In the sense that I didn't know what to do, and so that felt like that gave me some leeway. Remember that I actually don't know if this is getting me close to the optimum, right? All I can do is give you some guarantees, but I don't actually know what the optimum is in this case, right? At least I can tell you, I mean, I know what the capacity of this is. And by the way, the analog network coding, this is maybe something I should have emphasized a little bit. Where was it? I was just giving this little example here, but the analog network coding gets me not to just a bounded gap, but actually gets me to a gap that goes to 0, and not just an item per degree of freedom. It actually gets to capacity. If the growth of the SNR is with the transmit power, not with the gain. Okay. So I know, if you will, the capacity of the overall network, and then I sort of go back to I'm sort of mapping it back to the problems I had before by just doing this this cute little lemma, which is not surprising, right? It's just by a little unsurprising lemma. I would not claim to say that this was a good approximation to solving NP-complete problems. Maybe there is a way, but I'm not claiming anything even close to that generality. Okay, but that's a good question. Yeah, John? Yeah.
Could you use this idea to make a rateless joint source network coding system by allowing you to have retransmission of, you know, like request. You keep getting copies until you get enough.
Yeah. So, so my facile answer again is going to be, I don't know. However, I mean, there is a component that you would need for a rateless system that we don't have here. We don't have feedback. Right. So this is totally open loop. I just send it, and then I'm just giving you some construction. I mean, if I have feedback, then it would also depend on whether I have continuous feedback, in which case, you know, you can look at some of the things, for instance, that Tara has been doing in terms of, you know, building faster codes. Or you can, if you think that you only have feedback upon completion, there's, I'm sorry, I'm going off track. Should I just keep going? And am I going too long?
No.
Oh, okay. So if you're looking at reconstructions, I mean, so I'm thinking aloud, but you can look at things like, you know, modifications of norm. So I mean, you're a protocol guy, so. And basically there, what would happen is in those systems, what you're doing is you're getting feedback from only certain of your receivers, but that's giving you infer then something about the other receivers, right? So maybe you could do something like that, and they're sort of their extensions to norm, right? With coding, actually, that you can do, like SMART and some other approaches. So maybe I could imagine that then you might be able to do much better, possibly, right? Because I mean, those really, whenever you have the feedback, usually do much better. I don't know if that answers your question. I mean, these are just,
I just thought,
yeah.
When you have this distortion method,
right.
the idea of rateless becomes a little.
Right. Yeah.
It seems like it could fit in there because you have the sources you're suppressing. You could, you know, request
yes.
new information from them. You have the mixing in the channel. You have other copies there. Lots of possibilities.
Oh, you could imagine suppressing different sources given the feedback. I mean, I think there's all kinds of, yeah, absolutely. I think there's all kinds of interesting things which we haven't looked into at all, as it's evident from my first answer of, I don't know. Okay.
Okay, I guess the audience
Thank
is ready for
Yay, thank you.